I bet almost everyone got the correct answer. Clearly, population density is represented by just a scalar quantity. It's a single number at any point in space. Ground level air pressure, not a vector either. Acceleration of gravity, well, it points down everywhere, but it is a vector, right? So C is the only plausible answer, and that is what 3/4 of you got. So very good. So yes, we are going to talk about electric and magnetic fields, and these are vector fields. So somewhere, everywhere in space, there is some value of the electric and magnetic field. No matter where you are, it has some value at any moment. Now, electric fields are created by the presence of electric charges. Just having them around gives you an electric field. An electric field can put a force on an electric charge, as we'll see in great detail today. Now, next week we'll talk about magnetic fields. Magnetic fields are caused by the motion of charges, not by just having a charge around. And a magnetic field puts a force only on a moving electric charge. So they're a little bit different. Anyway, we're going to focus on this today, electric fields, electric forces, the energy due to the electric field, etc. Okay, so suppose we have what we will call a uniform electric field. Uniform just means it's the same everywhere, right? And we can represent that wherever you go, like here, there's a vector pointing to the right. And that is the value, we will say, of the electric field at that point x, y, z in space. In this case, our electric field vector function is very easily represented by E times the x hat direction. X hat, remember, does not carry any units. It is a dimensionless unit vector pointing in that direction. Just tells you the direction. That's it. So you don't have to worry about its units. We're going to talk in detail about what are the units of the electric field. Now, when we represent a uniform electric field, in this lecture and later in your DLs and problems and so forth, we're not going to sit and draw 100 arrows like this. That takes too long. So we're just going to draw one arrow and say we have a uniform field pointing in that direction, and we're going to call it E with the little vector symbol on top of the E to remind us that it is something that has a direction in space. Okay? So that's how we'll represent a uniform electric field. And now, what's it good for? What can we use this electric field for? Well, if we have a test charge, Q, we can sense the presence of our electric field. How? Well, an electric field puts a force on a test charge. If the test charge is Q, then just multiply Q times the electric field, and that gives you the force, F. In this case, the force is in the same direction as the electric field. Now, this is handy because this tells us that we know how to deal with forces. You've taken Physics 7a, Physics 7b, and you know the basic mechanics of how forces work. This test charge might be attached to some mass or other, and so you can just treat that force on this mass as you would any other kind of force, like the gravitational force, for example, would be the same. We're going to see that they have very different magnitudes, though. So F is equal to Q times Z. This also tells us what? It tells us the units of the electric field. This is how we define electric field, in fact. It's the number of newtons you get per coulomb. Since force is newtons and charge is measured in coulombs, the electric field then is the number of newtons per coulomb at that point in space. So everywhere you go in this room, outside, outer space, if you had a test charge and measure the force on it at some time, you would know the value of the electric field at that point in space at that time. It's changing all the time, of course, because stuff is moving around. But we try to set up nice stable situations that we can understand with our simple physics laws. So we'll see how to make a uniform electric field in a little while. But we need to think about electric charges for the moment. Now, people discovered the electron in around 1896. And it was realized that the charge on it was negative, and that atoms or matter had electrons in it. And it was found that the charge on the electron was 1.6 times 10 to the minus 19th coulombs. Now, once the atomic nucleus was discovered, we understood that hydrogen, for example, is a proton with an electron going around. It was believed that the proton, the electron, represented the smallest possible units of charge there are, which we call E, this 1.6 10 to the minus 19th coulombs. But since the 1960s and in tons of experiments ever since, we've learned that there are smaller charges, in fact. And the proton and the neutron, which are inside the atomic nucleus, are themselves composite particles made up of smaller things that we call quarks. This is probably the only time we'll talk about quarks this quarter, but it's worth mentioning that a proton has what we call two up-type quarks inside it and a down-type quark. The up-type quark, bizarrely, has a charge of plus 2/3 that of the electron, the absolute value. So it's a positive charge, and a down-type quark has minus 1/3. So plus 2/3 plus 2/3 minus 1/3 gives you plus 1 charge for the proton, which is quite remarkable, right? And at first, in the 1960s, when this idea was proposed, people could hardly believe that there were fractionally charged particles inside the proton and the neutron. The neutron has one up quark and two down quarks. So plus 2/3 minus 1/3 minus 1/3 gives you 0 net charge. And we know proton is plus 1, neutron is 0 charge. This is truly remarkable. As far as we can tell, by smashing protons together with as much energy as we can at the Large Hadron Collider, and that's what I work on, we have not been able to see any substructure to these quarks. As far as we can tell, they're point-like particles, just like the electron. By banging electrons together at the highest energies we can, we don't see any structure inside electrons either. So in our theories, those are point-like particles. But for all we know, there could be smaller things still, and maybe someday we'll see them. But it takes very, very high energy to see very, very short distances. And the higher the energy, the shorter the distance. But I could talk about that anytime you like. But I thought you might like to see that a little bit for your general edification. So now, suppose we have a uniform electric field like this, and we have a positive charge. What do we mean by a positive charge anyway? We have positive and negative charge, right? So where did that come from? Anyone know who defined positive charge first and how it's actually defined? I mean, long before we knew about electrons, even before we knew about atoms or whether atoms were real things, people were doing experiments with electrical phenomena of various sorts. We knew about lightning. It was believed lightning was an electrical phenomenon, but certainly people had experienced for years that if you walk on a carpet and touch a metal object, what happens? You get a shock, right? That's an electrical phenomenon. So in the late 1700s, Ben Franklin himself defined what we mean by positive charge. And his definition was if you take a glass rod and rub it with a piece of fur, then, I don't know what they were doing back then in the late 1700s, but okay, it charges up the glass rod with positive charge. In fact, you can transfer that charge around. I'm going to put it on those two little pith balls there. There we go. Okay, after they unwind a little bit, oh darn, these things always get tangled up. Let's see if I can untangle them a bit. I'll untangle them and charge them at the same time. There we go. Ooh, that's a good one. You can see that they're pushing each other apart in space. If you knew the mass of those balls and the angle between the two threads there, you could actually calculate what the force is pushing those two things apart. Why are they pushing apart? Because they're both charged up with this positive charge that I transferred from this rod to those balls. So we got to try to understand this a little bit better. Now, we've only talked about an electric field so far first, and the force is equal to the charge times the electric field. So we have this force to the right. If we have a negative charge, we have the opposite force. It goes in the other direction. Because Q is negative. Q times A. If Q is negative and E points to the right, F points to the left. It's just from the property of vectors, right? If you multiply a vector by negative itself, it just points in the other direction.